Welcome back to ECE 220. We are in Chapter 5, which is op amps, and today we're going to try to create additional op amp circuits. We've already introduced the inverting amplifier, and we'll try to get beyond that. Before that, you need to remember your lab number 2 is this week if you're in Group A, and that's the first 4 sections of the class. Group B, you have to turn in your lab number 1 report, and everybody tomorrow, homework 6 is due. So doesn't matter which section you are in, tomorrow homework 6 is due. Lab 2, your Group B, your pre-lab for lab 2 is due on Saturday. And as I said, we're in Chapter 5, and if you need to apply for advanced standing, this is the month to do it. I want to start today again by showing you the big real implementation of an op amp, and then show you a model for that mess of parts, how we can more conveniently model that, and that's what I'm meaning by a realistic model of the op amp. Then we'll even go a step further and say, well, what's the ideal behavior that we would like? And we'll give some assumptions. We'll say the input resistance, let's just assume that goes to infinity. Let's assume that the gain A goes to infinity, and let's assume that the output impedance is 0. And that now gives us an ideal op amp behavior or model to play with. And many of these different circuits will actually behave very close to what they will behave in reality based on the ideal op amp model. And we'll go through an example of the inverting amplifier. We'll look at situations where it saturates and what that means in terms of how big of an input voltage can you actually apply and still get this gain or scaling behavior that you thought you should be getting. We'll then introduce some new circuits. We'll look at a summing amplifier. We can actually combine multiple signals and get a weighted sum at the output. Again, remember this op amp was created to give us an analog computer. And now we can do all of these operations, addition, subtraction, scaling. Then we'll look at, well, do we always have to invert the sign? We'll look at connecting up a circuit that produces a non-inverting amplifier. And then we'll look at combining those two pieces, inverting and non-inverting, into a difference amplifier. That's where we're headed. I'm not sure we'll get all that way, but let's begin. Here's the realistic model. And again, this is a model of the op amp, and we're now trying to minimize the analysis that we perform. You're familiar with some of the models. We've done Thevenin equivalence, Norton equivalence. Now instead of having to analyze this 22 transistor, 11 resistor, 1 diode, and 1 capacitor circuit with each circuit that we build around an op amp, we can now replace that complicated circuit with a more reasonable model that involves a dependent voltage source. We have an input resistance, R sub I, between the inverting pin and the non-inverting pin of our op amp. Not shown here is the power supply that makes this operate or allows it to operate, but that has to be turned on. And then based on the difference between the non-inverting voltage and the inverting voltage, we get a scaled version at the output, and we also actually have an output impedance. We won't be using this until sort of after we've looked at how to analyze circuits in a more ideal scenario, and we'll find that we don't have to many times even go to this level of detail to analyze our circuit in terms of replacing an op-amp with this triangle that is associated with a dependent source, a resistor at the input side, and a resistor at the output side. These are the realistic model, and here I'm emphasizing model parameters. We have an input impedance, which is big, in the megohms possibly range. We have an open loop gain that's also large, 10,000 or bigger, usually 10 to the fifth. And we have an output resistance that isn't that big, but maybe it's in the teens or hundreds. But we could then model this complicated mess of a circuit with a more realistic model and interconnect this model with the external resistors and eventually capacitors that we've talked about doing in the future. But even before we get there, we can look at an ideal op-amp. In the ideal case, we make some assumptions. We actually let the input impedance go to infinity. And what does that allow us to do? If we let the input impedance go to infinity in this particular circuit, if we let R sub I go to infinity, what does that do for us? How do we think about or understand what happens when R sub I goes to infinity? What would that be like? That basically opens up that resistor, doesn't it? If we just remove that, we would have infinite impedance. Now we have no current flowing for I sub n or I sub p, and that gives us our input current constraint. So here, when we think of the input resistance going to infinity, we have an input current constraint. Which really translates into us saying that we have zero current going into the input terminals of an op-amp. If we actually let the gain, the open loop gain of our realistic model go to infinity, that gives rise to an input voltage constraint. Which says that we can get an output for a very tiny input, and in the limit, as A goes to infinity, that says that the difference between these potentials or voltages at the input pins of our op-amp, that difference goes to zero, or that allows us now to say that V sub n is equal to V sub p. And we could then simply draw our op-amp like we've been drawing or have drawn so far as this triangle with some input pins, the inverting input, the non-inverting input with a voltage V sub n and V sub p, and the output pin with current directed as I sub 0. The convention is to have all of these currents flowing in towards our op-amp circuit or symbol. So let's use that information now to analyze some problems. Let's look at the inverting amplifier, which is sort of the workhorse that we'll be playing with, but now we have to power it up. We have to energize it. That's what this VCC and V sub EE, you'll see this referred to many different ways, but you have a positive power supply voltage and a negative power supply voltage, And the negative power supply voltage could in fact be 0. Or it just needs to be less relative to than the positive polarity. Here we're setting them at two equal extremes, plus 15 and minus 15. And we've put some external resistors around these various pins on our op-amp. We're applying a voltage, V sub S, into the inverting pin of the op-amp, and we have some output V sub 0 across some output voltage V sub 0 across an output resistor R sub L. To analyze this, we need to give a little bit more information. So we're letting the power supply rails be the plus 15 and minus 15. We let the input resistor R sub S be 5K. The feedback resistor be 20K. And let's just assume that the input voltage going into the inverting pin on our op-amp is set at 2 volts. And we're assuming an ideal op-amp scenario. We're assuming the input impedance or input resistance is infinite, A is going off to infinity, and we don't have to worry about the output resistance of the op-amp. If that's the case, how did we start saying that we would approach the analysis of such an op-amp circuit? What's the very first step that we need to make as we're examining the analysis of this circuit? What are we looking for? Do you remember? What's the key? Feedback. We need to see, is there feedback from the output pin to the inverting pin of our op-amp? Do we have negative feedback? And in this case, what's the answer? Yes, we do have a resistor taking that. If we didn't have that negative feedback, this poor op-amp's going to saturate. It's going to be either at plus the positive supply value voltage or the negative supply value voltage. If we didn't have that feedback resistor, this poor op-amp is going to want to just go to plus 15 or minus 15 depending on what it sees at its input terminals. It will saturate. Now we have feedback, so there is some hope that this won't just be banging or stuck at one of the supply rail voltages. So our first step is to actually acknowledge that we do have negative feedback. And now we can continue with the analysis process. And last time, what did we talk about? Now that we have feedback, what's our next step in the process? And we just came out of chapter 4, where we were applying some of these analysis tools. We had mesh current analysis and node voltage analysis that we were playing with. It's maybe a little bit more challenging to see meshes in this diagram, but what if we now, in step 2, concentrated on learning how the currents are responding at that particular node? Can we write a KCL equation at the inverting input pin? Here is V sub n, and when I write V sub n, I'm really meaning that that's this voltage between that pin. If I now had my measuring leads in the lab, I would put my positive lead at the pin, the inverting pin of the op-amp, and my negative lead at the reference node. And I also have this polarity, which is V sub p, that now if I'm assuming ideal op-amp behavior and with negative feedback, I can now say I have that voltage input constraint, or input voltage constraint. But before I do that, let's now look at KCL at that node. If I now said this is I sub s, this is now I sub n, and this, let's just say, is I sub f. Now you can write a KCL equation for that. KCL at V sub n is the sum of the currents in equal the sum of the currents out. I sub s is going in, I sub f is going in. Those sum up and those equal what's leaving that node, which is I sub little n. That's KCL. How do I express I sub s in terms of the voltages and resistors? See how all of this analysis techniques or strategies are coming into play as we advance through the book or the material. I sub s is just Ohm's law. That's the voltage dropped from left to right across R sub s divided by R sub s, which is V sub s on the left minus where we're going, which is V sub n, divided by R sub s. That's I sub s. What's I sub f? Using similar thought process, isn't that V sub 0 minus V sub n divided by R sub f? And what is I sub n for an op amp? What's the input current going in, or what's the current going into the inverting input pin? It's hard to get in there, isn't it? Because the resistance is so large. I sub n is 0. We put all of that together, and now we can write that KCL equation a little differently. We said this is V sub s minus V sub n over R sub s. That was I sub s, plus V sub o minus V sub n over R sub f. And that's equal to 0, and that was due to this input current constraint. And the output voltage constraint, not output, what am I doing? Input voltage constraint. When I say input, I want to say output. When I say input, you say, no, sorry. So here we needed to say when you say input, you say input. Now we have the input voltage constraint. Which says that V sub p is equal to V sub n. And now let's go back into the circuit. And can you say anything about either of those by inspection of the circuit? What is V sub p? Where are we connecting the non-inverting pin of our op amp? To the common node, which is what we're saying is 0. That's our 0 volts. That's what we're connecting with a wire to the non-inverting pin. That's now at the reference voltage, or the common voltage. V sub p is now 0. This is now 0. And if V sub n is equal to V sub p, with a going off to infinity, now we know that V sub n is 0, which allows us now to simplify this, and we can rewrite that. If we pushed the V sub s term on the other side, we have V sub 0 over R sub f is equal to minus V sub s over R sub s. And we actually want a voltage gain. We want to know if I put in a V sub S, what's going to pop out at V sub O. We want to look at this ratio of V sub O over V sub S. Let's divide both sides by V sub S. And at the same time, let's multiply both sides by R sub F. Or this relationship now leads to the gain that we were wanting, or the relationship that we were wanting, to establish between our input voltage and the output voltage. Now we can actually go on to step 3 and solve for V sub 0. Now we want to put V sub S back onto the other side, and now we have this relationship for the output voltage. Did I give some numerical values for this? R sub F was 20K. R sub S was 5K. Aren't those numbers convenient? Now we have 20 divided by 5, and we multiply by V sub S, which I think I said was 2. What's the result of that computation? 4 times 2, or now we have minus 8 volts. Are we finished? The output voltage is minus 8 volts. Is it? What's our final step in the analysis of these op-amp problems? We made an assumption. We assumed that our op-amp was operating in its linear operating range. Step 4 says check to see if that still remains true. Is this voltage now outside or beyond our supply rail voltages? That's step number 4. Step number 4 says we need to check. We have V sub 0 as minus 8 volts. And is that within minus 15 and plus 15? Is this actually bigger than the lower limit, which is our lower supply voltage value of minus 15? And it is. It's less in magnitude than 15. That says then that the output in this given scenario, the output does not saturate and consequently, we can conclude that indeed the output voltage of that circuit is indeed minus 8 volts. What are some observations that we can make relative to the analysis that we just performed? If I looked now at the V sub 0 expression, the functional expression for V sub 0, if I now look at this, how is that? Is A in there? Is V sub 0 a function of A? Or do I need to put another word in there? Do you see A anywhere? The gain, the open loop gain? No. We were able to get rid of that, so this is not, V sub 0 is not a function of A. That's a good thing. V sub 0 is only a function of those external resistors, R sub F and R sub S, that we connected around that op-amp. V sub 0 is only a function of the external resistors. And in fact, V sub 0 is independent of R sub L. This one can kind of come back to bite you because you didn't see R sub L in there, but it can kind of come back because of how much current can we get out of this op-amp circuit? Unlimited? Is that poor little op-amp able to support 2 amps coming out of it? No. You'd have to go back to the data sheet, and the data sheet now maybe says, oh, the maximum current at the output is 40 milliamps. So what's we need then, that puts a constraint on the size of that load, the size of the resistor that we can hang on to the output pin. If we're demanding that we have more current flowing than 40 milliamps, we're not going to get it, and so the voltage is going to actually be less than what we expected. It just can't quite supply that much current. We can get a feel for how big R sub L or how small R sub L is if we plug in some numbers. In our case, we had a supply rail voltage of 15. And what was our, so now I'm just using Ohm's law. I know that V sub 0 is equal to, well, that's sort of what I'm using or working from. If I solve that for R sub L, I have V sub 0, and V sub 0 can only be as big as a supply rail voltage, which is 15 in this case. And I sub 0, that can only max out at 40 milliamps. And if you do the numbers, this ends up being, now we have 15 divided by 4 over 100, or 1500 divided by 4, or 375 ohms. If somebody now tries to put a load resistor on that circuit of 100 ohms, guess again when you try to find V sub 0, it's not going to be what we calculated as -8. So you might see something different if you now tried to load that op-amp circuit with a very low valued resistor, load resistor. So we're assuming that this is going to be 375. What if we said, well, we had our supply rail voltage of 12 volts, and again we had this 0.04 output current limit. Now what's the value of our smallest load resistor? Now we have 12 divided by 0.04, or that's now 300 ohms. So it's going to depend on our supply voltage, what that lower limit is on our load resistor. But just be aware that if you connect a very small resistor to the output pin of that op-amp, you may get a very small dribble of current out. You can only get 40 milliamps out, and so your voltage may be a lot less than what you calculated. That's the warning I want to leave you with. But if we assume our load resistor is bigger than 375, then what's the output of this circuit really looking like? What is V sub 0? If we keep R sub L bigger than 400, what's V sub 0 going to look like to us? If we now just start connecting different resistors to it, what's V sub 0 going to, or what's this circuit going to look like? How's it going to behave? If we've now put a 2 volt V sub S We've hung these external resistors around it at that of those values. What do we see at V sub 0? What does it look to us? If we opened this up and said, there are the pins, V sub 0, what's V sub 0 going to look like? That's the last observation. The circuit acts like an I know you were wanting to say this. I could just hear it virtually. An ideal voltage source. It's giving you what we just calculated, minus 8 volts. And it will do that for all these resistors that we apply to it at the load as long as they are bigger than 400. It's going to appear as an ideal voltage source. What are the limits on V sub S in this particular case? How big could we go with the input voltage V sub S before we saturate? That's what I'm trying to establish here. What are the limits on V sub S? What are our output? What's our output limited to be between? What's V sub 0's limit? Is it going to go to 20? Is it going to go to 30? How big of a score can it get? Can we run up the score? What's it constrained by? V sub 0. I'm giving you gestures. Do you not see what those are? The battery. How did we connect this? How did we power up the op-amp? With the plus voltage supply rail and the minus voltage supply rail, we know that V naught, the output voltage, cannot go beyond those two values. In this particular example, we said we had a positive output supply of 15 and we had a negative supply of minus 15. We know that V sub S can't be anywhere outside of those. And in practice, it's a fraction of a volt probably inside that window. So you're looking at minus 14 to plus 14 possibly, V sub 0. Let's just assume we can go all the way to the rails. But we do have a connection, a functional form for V sub 0 and our input voltage V sub S. That we said was minus R sub F, R sub S, V sub S. And for this particular case, we had minus R sub F and R sub S really just being minus 4. Didn't we? Or we now have minus 15 is less than minus 4 V sub S is less than 15. And now we can do the math. We can do the algebra. We know if we divide by a negative number, that changes the inequality direction. So now we have this 15 over minus 4. V sub S is going to be bigger than that. And it's going to be smaller than minus 15 divided by minus 4. Or this is now minus 3.75 and this is 3.75. Or we know the limits on V sub S. If we go beyond that, if we applied 4 volts, then we would saturate and we would hit the rail. Here, as long as we keep V sub S less than 3.75 and bigger than minus 3.75, we're okay. Let's look at that a little bit more in example 2. Example 2 now says, what kind of a circuit do we have? An op-amp circuit. Correct. Let's go just another step further. Negative feedback. And what's the functionality of this operational op-amp circuit? How is it going to behave? What do we know? The way that this is now connected, what do we expect to happen at the output? It's the only amplifier circuit we've talked about so far. This is inverting, isn't it? It's an inverting amplifier. So let's now assume that we have this with the following values. Now suppose that we have 4 volts applied at V sub S. Hint, hint, I think now you can remember we had some ranges on V sub S before. But let's just go ahead and analyze this. We now have V sub S of 4, R sub S is 5K, and R sub F is 20K. And suppose that now our supply voltages are what they were before, plus and minus 15. We know that V sub 0 is bounded by those supply rail voltages. V sub 0, though, in this inverting amplifier configuration, functionally is minus R sub F over R sub S times V sub S. We know that to be true. That's the inverting amplifier. We now plug in the numbers. We have 20K over 5K times 4. Or we now have minus 4 times 4, or minus 16 volts. We were able to do this calculation because we did notice that we did have negative feedback. So then we said, okay, let's use our inverting amplifier formula. Boom. We now come up with an answer of minus 16 volts. But we can't forget step 4, especially on the exam. This is how you could get tripped up on these multiple choice, right? You could say, oh, there's an answer. It's minus 16, and it's one of the ones. Is that actually what we will see out of this circuit? No, because that's beyond our supply voltage rails. We know that V sub 0 being minus 16 volts is less than minus 15 volts. That says that our output is actually saturating. And we now have to say, well, the output is actually going to be clipped. You might hear this word used occasionally. Now the output is clipped at its lower limit, its negative supply rail voltage of minus 15. Now, using this circuit, you have R sub F of 20, R sub S as 5. V sub S now I want to vary. I want you to now, oh no, I'm changing it up. Woo! Good thing I scrolled down. Here's your task. I want you to complete this table. For the different input voltages, V sub S, give me the output voltages, V sub 0, for these different values of V sub S. And this isn't that hard, but you just need to kind of pay attention. So I'll give you a couple of minutes to pull out your calculator or your phone or whatever and calculate that output row in the table for those different V sub S values. And you can work together since this is not an exam. Is everyone finished? I take it by that lack of a response that you're not quite there. Are you at least using a gain, a scaling factor of 12.5? And this is an inverting amplifier. This is now minus 12.5. What did you get for 0.4 volts? What was your answer? 5? Really? -5? Okay, now we're inverting. Scaling was correct, 0.72. -9, 2. -25. Oh, that saturated, didn't it? And our supply voltage, the negative supply voltage, was -10. It wasn't equally spaced like the positive was +15. So now we saturated at -10. What about -0.6? I hope you calculated this. 7.5. That's still less than 15, isn't it? -0.8, 10, which is still less than 15. What about -2? If we hadn't hit against the supply rail, we would have said, oh, it's 25. But now we have a 25 coming at us from the formula, but then we have to realize that that's hitting the rail. And now the positive supply rail is different than the negative supply rail in terms of its absolute value. Questions on that? Is that clear? On the exam, can you quickly do this and say, wait a minute, step 4, I need to remember step 4. I need to check to make sure that I'm not saturating, because that would be an easy additional answer to supply on the exam, is to say 25 volts or -25 volts, and then you quickly calculate it and you go, there it is, that's my answer. Ouch. Wouldn't work. So, what's our range now for V sub S? What can we now ahead of time, instead of just going through and blindly calculating these numbers, could we now sort of already pre-compute what V sub S needs to live between so that we don't saturate at the output? We know this is true. V sub 0 has to live between the supply rail voltages, and those were set at -10 and 15. But V sub 0 is -12.5 V sub S. And now we simply divide that out. We now say, oh, this is now going to be 15 over -12.5. (15) divided by -12.5 is now -1.2. And thank you for correcting. This is now -10 over -12.5. That's less than 1, and in fact it's 0.8. In this case then, V sub S is restricted to being less than 0.8 volts and bigger than -1.2 volts. It doesn't have to be symmetric. its limits on the input voltage, because the output, depending on the supply rail voltages, might not be symmetric about a given common value. Well, that was fun. Let's now take it up a notch. Now, do you see what I have? I have actually made this circuit a little less complicated because I've avoided the circles. I've avoided drawing these independent voltage supply sources, but they're there. I have a source at V sub A, a source of V sub B, and a source of V sub C. Those three are going into this circuit through different resistor values, R sub A, R sub B, and R sub C, and I have an R sub F. How are we going to approach the analysis of this problem? What's our first step in analyzing an op-amp circuit? Step one. Do we have negative feedback? Do we? Is the output pin connected through a resistor back to the inverting pin of the op-amp? Yes. We do have negative feedback. Now we can assume that we're in the operating region, and what would be our strategy? So the first step is we now have concluded that we do have negative feedback. What's the second step? We've been focusing on KCL at the inverting pin of the op-amp. We have this current going in, I sub N. We have this current, I sub F. And we have this current, we have this current, and we have that current. Now we're getting a little more interesting, aren't we? Is that a question? Okay. It's a wave. No, I'm sorry. I'm embarrassing people. But we have to kind of stay loose, stay awake in this class, huh? How do we do KCL? What's V sub N? What's V sub P? Would you just slow down with the questions? What's V sub P? 0. What's V sub N? 0. So this is 0. This is 0. Now we can write KCL based on that 0 voltage value. So now we have KCL at V sub N is now going to be 0 minus V sub A over R sub A. Is it clear where that came from? That's the top current going to the left. 0 minus where I'm going, which is V sub A, divided by R sub A. The middle current going to the left is I sub B, but that I'm going to write as 0 minus V sub B over R sub B, plus 0 minus V sub C over R sub C, plus 0 minus V sub 0 over R sub F is equal to 0. And now I would like you to solve that for V sub 0. Put V sub 0 on the other side, multiply everything by R sub F, both sides, and you end up with minus V sub A over, R sub F over R sub A, V sub A, plus R sub F over R sub B, V sub B, plus R sub F over R sub C, V sub C. Interesting. Now we have an inverting summing amplifier. Now we can have multiple voltage sources scaled differently and creating a single output. Yes? So the last one yes, so let me change that. The question was, let me just say that. The question was, wasn't your I sub f in the wrong direction, but I didn't write my equation right relative to how I had drawn my current. So now let me draw that going to the right, and now I have 0 minus V sub 0 over R sub f, and hopefully that's now okay. We'll pick up there with another few amplifier circuits tomorrow.